one example. I'm proposing a very simple example in this case because I really want you to see things. Now, what I'm doing in this case, I'm projecting the entire stress into the shear direction. This is not quite a realistic case, but if you want to think about it in terms of the, if you want to think about this in terms of the uniaxial test, for example, if you have a bar and you have one force or probably a distributed force on this end here, and you want to project this into only shear, think about these forces trying to cut this across this line here. So on the surface of this line, you will have the entire stress acting as a shear force. Okay, now if you cut it in this direction, this is going to be projected completely in the normal direction. If you cut it in the other one, it's just going to project inside of it. So this can be the case now. I mean, in 3D, this does not make sense. I mean, this is probably possible to make for a 1D example, but we are solving things in 3D, so it doesn't make much sense. However, I'm still going to do it in this way for you to see things. Now, let us assume that we have this stress tensor. I'm just going to solve this example for everything we have done so far. I'm just going to find, first of all, the shear stress on this specific plane. So I have the stress tensor, and I'm interested in finding the shear stress on this specific plane. And then I'm interested in finding the maximum and the minimum normal stresses. And then I need to find the maximum shear stress and the plane where it is actually acting. Okay, so for the first part, I need to find the shear stress on this specific direction. So this is basically this problem here to be solved. Again, this is the first example I've discussed. You are going to need to find the, first of all, I've been using this too many times. So you first of all need to find the stress vector on this specific plane. Then you need to find the normal components of that, and then you need to find the shear component of that. So this is what is required for the first part, asking for the shear components on the specific plane. Then in the second part, it is asking to do the maximum normal stresses. We said the maximum normal stresses are going to be the eigenvalues. So we need to solve for the eigenvalues and their directions. So the value of the maximum normal stress and the direction where the maximum normal stress is going to happen. And then at the end, it is asking us to do the maximum shear stress, or the maximum possible shear stresses. I've been writing everything in here. I'm just going to add the equations for the maximum shear in there as well. So I'm just going to call it TS max. TS max is going to be T1 minus T3 divided by 2. And on this specific plane, TNS max, I have some normal stress. This normal stress is going to be T1 added to T3 divided by 2. And the normal direction where this is going to, or the normal direction, the plane where this is going to happen, is just going to be NS max is equal to plus minus 1 over square root of 2 multiplied by N1 added or subtracted from N3. Okay, so this would be then the first part of this example. So I'm going to solve it now. If you have any questions, just ask or let me know, and then we can discuss your questions. So first of all, I need to find, I just copy the material from here. So I've got the stress tensor. Everything is 0 except for sigma 1, 2, and sigma 2, 1. And then I have this normal direction. So I'm just going to write them down here. So first of all, the stress tensor is 0, 100, 0, 100, 0, 0, 0, 0, and 0. This is the first thing. Then I have the normal direction. It is 1 over square root of 2 of E1, the first basis vector, added to E2, the second basis vector. Now, the first basis vector, 1 over square root of 2, I'm just going to write them down. So it is 1, 0, 0, and the second basis vector is 0, 1, 0. Right, you agree with that? And then n is going to be 1 over square root of 2, 1, 1, 0. Okay, so the first part of this question is to find the shear stress on this specific plane. To find that, we need to multiply and find Tn small, and then multiply it again, and find the Tn, the normal components, and then find the shear components. So first of all, Tn vector is equal to 0, 100, 0, 100 again, 0, 0, 0, 0, 0, multiplied by 1 over square root of 2, 1, 0, and 0. Just going to remove this from here, so I have more space for myself. All right, so just multiply them together. You have 1 over square root of 2. This is going to come first. Then you have 1 multiplied by 0. Sorry, this is not 0, this is 1. 1, 1, 0. So it's 1 multiplied by 0, 1 multiplied by 100. This is going to be 100, and then you have 0. You come to the second part, 1 multiplied by 100. This is 100 added to 0 and 0. And then you come to the last line. This is 0, 0, and 0 is going to be a 0 there. Okay? So just a vector matrix multiplication. Now you have the Tn. You need to find Tn. This is the normal component. You just multiply Tn again with the n. So this is 1 over square root of 2. This is the dot product, so you need to write this guy, you need to write it as a row matrix. Okay, so just to do the dot product. So it is 100, 100, and 0 multiplied by 1 over square root of 2, 1, 1, and 0. This is the normal guy. Now this is the normal, right? This is the normal here. So you have 1 over square root of 2 multiplied by 1 over square root of 2. This is going to be 1 over 2. And this is added to 1 multiplied by 100, added to 1 multiplied by 100. This is going to be 100 added to 100, added to 0. Or this is going to be basically 100 in its respective units, megapascal in this case. So the normal component on this plane is going to be 100. Now I need to find what is the shear component. To find the shear component, I have Ts squared is equal to Tn squared minus Tn squared. Now this one, I know it is already written here. This is the 100. This one here, this is the square root of the sum of the squares. So I'm just going to calculate the square root of the sum of the squares. Just to remember the vector, just going too far. So this is the Tn, this is the Tn here. So the square root is going to be 100 over square root of 2, 100 over square root of 2, and 0. This is the first one, this is the second one, and this is the third one. And everything is divided by 1 over square root, is divided by square root of 2. So Ts squared is 100 over square root of 2 squared added to 100 over the square root of 2 squared added to 0 squared. I'm taking the square root of this and then squaring the whole thing. You remember I said this is the square root of the sum of the squares. So this square will cancel out with this square root, and I will be left with whatever I have inside the square root. This is basically 0, so I'll get rid of it. And then I have this guy here, this guy is 100, it is 100 squared. You remember the 100 here? This is the 100. So minus 100 squared. Now, square root squared is 100 squared divided by 2, added to 100 squared divided by 2. I'm just taking the square for this guy, but this 100 is the same here, so I'm just going to keep the square on top. So it is half 100 squared added to half 100 squared, subtracted from 100 squared, and this is going to be 0. So TS squared is basically 0 on this plane. Right? And it makes sense because you remember when I said the entire thing is 100. So you project this into the normal direction, and the normal direction is 100. You cannot get anything larger than that. This is the end of it. You don't have anything left to be projected in the shear direction. Okay, so it makes sense. Now, we have done the first part of this example. So for the first part, I'm just going to clear this. So the shear stress on this plane is equal to 0. I have found the first part. Now I need to do the second part. Maximum and the minimum normal stresses and the planes which they are active on. Okay, so to do this, I need to find the solution for the eigenvalue problem to find the principal stresses. We're going to solve one 3D eigenvalue problem. All other eigenvalue problems are solved exactly in the same way. I'm going to solve this example. Next, I'm going to ask you to solve the example, solve another example yourself. And I'm going to show you the solution, but I will leave you quite a few examples more in the tutorials with solutions. Okay, so now I need to solve an eigenvalue problem. The stress matrix looks like this. Probably just please pay attention because, as I said, I mean, this is nothing in YouTube, but just probably from my past experience, I found that people get confused with it. So I'll try to explain it once. Hopefully you will get it. So you have this stress tensor. And you are interested in finding the eigenvalues. To find the eigenvalues, you subtract lambda from all diagonal terms, and you make the determinant equal to 0. All right, so the matrix then is going to look like this. I'll probably just try to keep the determinant and just take 0 out of this and leave the lambda there. Here I have minus lambda, minus lambda, minus lambda. Now, if you have a number in there, you don't have a 0, you just keep the number in there. Now, the determinant of this, you can expand this in whatever way you want. I'm going to expand it in this direction, but you can expand it in this direction or in this direction. It doesn't really make any difference actually. All right, you know how to find the determinant of a matrix. I mean, is a standard procedure. You would find a lot of description for that online. I'm just going to do it, but if you think this is something you probably forgot, then probably just search for that online. It's easy to find. So I'm going to expand it in any direction I want. Probably the easiest way is just to expand it for this direction or this direction. It doesn't really matter. Now, for later examples, it is better to expand it using this column or this row, because then you have lambda multiplied by a quadratic lambda, so you end up having a linear equation multiplied by a quadratic equation. You know how to solve the linear one and how to solve the quadratic one. So it's easy to do it this way. If you don't do it in this way, it's very likely you end up having a cubic equation like I'm going to have now, which is going to be more tricky to solve. Okay, I'm going to explain the linear multiplied by quadratic procedure in the next example, but for the time being, I'm just going to do the cubic equation because this is very easy. You'll see that this is quite easy to solve. So I'm going to expand in this row here. So to expand, this is plus, this is minus, this is plus. you have, first of all, minus lambda multiplied by the determinant of this part. So it is minus lambda 0, 0, minus lambda. And then you have minus 100. See here I have plus minus, so the minus will be left. Here I have minus plus, so the minus will be left. Multiplied by, I'll cancel this one and this one, so I'll be left with 100, 0, 0, minus lambda. And then this is added to 0 multiplied by the determinant of this part, which is 0 anyway, so I'm not going to consider that. All right, so I have minus lambda multiplied by the determinant of this. This is basically minus lambda multiplied by minus lambda is lambda squared subtracted from 0. So I have minus lambda multiplied by lambda squared minus 100 multiplied by minus lambda multiplied by 100. So it's minus 100 lambda, and you subtract 0, is not going to be anything. So this is the equation I need to solve. So this is basically 0 equal to minus lambda cubed. And you have minus 100 minus 100 is going to be plus 10,000 lambda. All right. So to solve this equation, I'm going to convert it into quadratic and a linear equation. So I have 0. I will take lambda as a common factor. I will be left with minus lambda squared added to 10,000. Just take lambda as a common factor. And then this multiplication is equal to 0. It can be equal to 0 only if this guy here is equal to 0 or this guy here is equal to 0. If none of them is equal to 0, it is not possible for this to be equal to 0. This multiplication is the only possibility that either one of them is equal to 0, or probably both of them are equal to 0. Otherwise, it is impossible for this expression to be equal to 0. All right? So if this part here is equal to 0, this would mean lambda is equal to 0, and this is my solution for the linear part. If this part here is equal to 0, then I have minus lambda squared added to 10,000 is equal to 0, or basically I have lambda squared is equal to 10,000, and this would mean lambda would be equal to plus minus 100. And the square root of 10,000 is 100 plus or minus. Now I have three values for lambda. I have the possibility for lambda to be 0. I have the possibility for lambda to be minus 100. I have the possibility of lambda to be plus 100. I'm just going to put them in order. I'm going to start with the maximum number, which is 100. Then the second number is going to be 0. And then the third number is going to be minus 100. Just put them in this order. So I'm going to call T1 equal to 100, T2 is equal to 0, and T3 is equal to minus 100. So far, I have been able to solve the first part. This is the maximum and the minimum normal stresses. So I have 0, or let's probably just put them in order, 0 and minus 100. Now I need to find the direction of the planes for each one of these. So I need to find N1, N2, and N3. All right, because each one of these normal components are active on a specific plane, are only available on a specific plane. So I need to figure out where are these planes. So to find the direction for T1, so for T1 equal to 100, you remember I took lambda and subtracted from the diagonal terms. Okay, it's here. It's ugly now, but try to bear with me. See, you have the minus lambda here, right? Here you still don't know what is lambda. You don't know that yet. Now you know that lambda is equal to 100. So I'm going to substitute lambda with 100, and find the direction of them. So what I'm going to do is just subtract lambda with with 100. I've got minus lambda here, so it is going to be minus 100. And then I have 100 and 0. I have 100 minus 100 and 0, 0, 0, minus 100. Right? Because I'm subtracting lambda, so lambda is 100. It's going to be minus 100. Now, the direction of this is n1, n2, and n3. I don't know them, all right? I don't know what is the value of n1, n2, and n3, but I know that this multiplication should be equal to zeros. So multiply them, you get 3 equations with 3 unknowns. The standard procedure. I have minus 100 n1 added to 100 n2 is equal to 0. I have 100 n1 added or subtracted from 100 n2 is equal to 0. And finally, I have minus 100 n3 is equal to 0. I have 3 equations here. I'm going to start from the easiest equation. So the easiest one is this one here. Is minus 100 n3 is equal to 0. And this is only possible when n3 itself is equal to 0. If it is not equal to 0, this is not possible to be equal to 0. There's only one possibility. That is n3 is equal to 0. I have the first component of my vector, this vector here. This vector, I've got the first component of that. Now I need to look for n1 and n2. Now the n1 and the n2 is the one that most of the people would find really confusing, because they end up having, they think they have 2 equations with 2 unknowns, but in reality, you have just 1 equation with 1 unknown. See, if you look into this equation, you see that this is exactly the same, just multiplied by minus 1. Just multiply this equation by minus 1, this will switch to negative, this will switch to positive, and you have the same equation. So if you try to solve 2 simultaneous equations, you will get nowhere. You will always get 0 is equal to 0, because you are repeating the same thing and trying to use it. So the way forward then in this case is you assume one of them. Now, having 1 equation with 2 unknowns, some people would think probably there's no solution for that, but in reality, there's an infinite number of solutions. For any number you assume for n1, you will get a number for n2. Assume that n1 is equal to, I will write it in terms of each other. So I will just take minus to the left and keep the positive to the right. I will have minus 1, or 100 positive n1 is equal to 100 positive n2, or just simply n1 is equal to n2. So if you assume that n1 is equal to 1, n2 will be equal to 1. If you assume n1 is equal to 10,000, n2 is going to be the same. You just assume anything you want for n1 and n2. It's completely up to you. Now, there's one restriction on you. I said you really want to normalize things, because you want to have the length of the normal direction to be equal to 1. Because as I said, you always try to find projections using the normal direction. If you have some length to the normal direction, you are going to magnify or probably scale down the forces you are looking for. So you always take the normal direction to be equal to 1. Okay, so in this case, I'm going to assume n1 and n2 are equal to 1. This is the easiest for me. So in this case, I will have 1, 1, and 0. I need to find the length of this vector. This is, remember, this is n1 vector. This is the first principal direction. I need to find the length of this. If the length is different from 1, I will divide by the length, and then I will bring the length back to 1. So the length of n1 is the square root of the sum of the squares. 1 squared added to 1 squared. This is basically the square root of 2. So for this length to be equal to 1, I need to divide by the square root of 2. All right, so it doesn't matter really anything you pick, any length you pick for n1 and any length you pick for n2. If you normalize, you will get back to this vector, this specific vector. It's 1 over the square root of 2 multiplied by 1, 1, and 0. So this is my N1. Now I repeat the exact same thing. As I said, we have been doing the whole thing for T1 equal to 100. I need to repeat the same thing for T2 and 3. So starting from T2, for T2 is equal to 0, we need to find N2. What is the value of N2? Again, I substitute lambda with 0. I have minus lambda is minus 0, 100, 0, 100 minus lambda is 0 and 0, 0 and 0 and 0. And this is basically the matrix I have when substituting lambda with 0. Now again, to find N2, I just need to find these components, N1, N2, and N3. Now these are the general components, and this is equal to 0, 0, and 0. Now again, some people will find this confusing, so just pay a little bit of attention because you may get confused if you don't get it now. So I have the first equation to be N1 multiplied by 0, N2 multiplied by 100. This is 100, N2 equal to 0. And then from the second equation, obviously N3 is multiplied by 0 again. And from the second equation, I have 100, N1 is equal to 0. From the third equation, and this is the probably confusing bit, in the third equation, you have 0, 0, 0 is equal to 0. So you have 0 is equal to 0. All right, now let us start from the easy bit. The easy bit is 100 N2 is equal to 0. So this would only be possible if N2 itself is equal to 0. There's no other way for that to happen. If you look into N1, you have 100 N1 is equal to 0. Again, this is not possible unless N1 is equal to 0. And then you have 0 is equal to 0. And you're trying to find N3. What do you think about the N3 then? Stating 0 is equal to 0. So your equation will always be satisfied regardless of N3. You pick anything you want for N3, this will not break the equation. The equation is always satisfied. So in this case, I'm going to pick anything I want for N3. I mean, if N3 is infinity, it's still going to work for me. But since I'm going to need to eventually normalize things, I'm going to take N3 to be equal to 1 because this is easier to calculate the length for. So in this case, if I take N3 is equal to 1, I have the vector to be 0, 0, and 1. This is my N2. All right, now if you calculate the length of this, this is the square root of the sum of the squared, 0 added to 0 added to 1 squared, and the length is already 1. So you don't need to normalize it, it's already normalized. So I've got the second normal direction. And this is for T2. So this is for T2. Now I need to do this same thing for T3. Now for T3, which is minus 100, what is N3? All right, so I again repeat the same thing. Minus 100, I have minus lambda there, so it's going to be plus 100. I have 100 there and 0. Here I have 100 and minus 100 is plus 100 and 0, 0, 0 and plus 100. This is multiplied by N1, N2 and N3, and this is equal to 0, 0 and 0. And these are the components of N3 vector. All right, so this is the components of N3 vector. All right, so from the first equation, I have 100n1 added to 100n2 is equal to 0. From the second equation, I also have 100n1 added to 100n2 is equal to 0. And from the last equation, I have 100n3 is equal to 0. So these two equations are exactly the same, just the same situation we have dealt with in the first case. And from the third equation, we know immediately that n3 is going to be equal to 0. So this will give us n3 is equal to 0. I've got the value of n3. These two equations are going to be the same conclusion out of them. I will have n1 to be negative n2. So again, I can assume n1 to be 1 and n2 will be minus 1, or just the other way around. It's completely up to you. It's not going to make any difference. Still going to identify the exact same plane. All right, so I'm just going to pick 1, minus 1, and 0 for n3. Again, I need to normalize, divide by the length, the square root of the sum of the squares, and the square root of the sum of the squares is 1 squared added to minus 1 squared added to 0, and this is going to be the square root of 2. This is basically I divide by the square root of 2 by the square root of 2, or I just simply write n3 is equal to 1 over square root of 2 multiplied by 1 minus 1 and 0. And then I have been able to find the planes where this is active. So this is 1 over square root of 2 multiplied by 1, 1, and 0. This is 0, 0, and 1. And finally, I have 1 over square root of 2. I have 1 minus 1 and 0. So this is n3 now. All right, so I've been able to find the maximum, the minimum, and the plane where these maximum and minimums are active. The left, or the one part that is left for us, is to find the maximum shear stress and the plane on which it is active. Yes, so this is the ones here. So the maximum shear stress is going to be T1 minus T3 divided by 2. And on the same plane, I have some normal stress. This is T1 plus T3. And if you are interested in the direction, then this is the direction. Okay, so let us use this set of rules. Ts max is going to be 100 minus 100. This is T1, this is T3 divided by 2. This is basically 200 divided by 2, or basically 100. And on the same plane, where I have 2s max, I also have 2ns max. This is going to be 100 added to minus 100 divided by 2. Again, this is T1 and T3 added to T3. And this is 0 divided by 2, or simply 0. So on the same plane, where I have this maximum number here, I got the shear stress at 100 maximum amplitude. On the same plane, I have nothing left for the normal, and this is the normal on the same plane is going to be 0. I'm just projecting the entire thing in the shear direction. All right. Now I need to find the direction, basically for Ts max, and then the direction is this set of rules. I'm just going to use them. And here I'm going to split. So I'm going to do it first for plus and then for the minus. All right, I'm just going to do it twice. I'm not going to mix up things so you can't see it easier. I got n1 to be 1 over square root of 2, 1, 1, and 0. And we've got n2, or n3, sorry, I'm interested in n3, is 1 minus 1, 0, multiplied by 1 over square root of 2. Right? Now the rule would say I have to add them together first, So added together and multiplied by 1 over square root of 2, I have ns max. All right, so I'm just going to take 1 over square root of 2, 1 over square root of 2 as a common factor and multiply it with this 1 over square root of 2. So this will give me 1 over 2. This is multiplied by 1 added to 1. This is 2. And then I have 1 added to minus 1. This is going to be 0. And then I have 0 added to 0 is going to be 0. So I basically just have here half multiplied by 2. And this is going to be 1, 0, 0. Now, I have here plus and minus, so I'm just going to add the plus and minus here. Remember? Oops, that. I said here you have the plus and minus signs. Okay, so I've been able to identify 2 planes where the shear is going to be maximum. The alternative to that is just to have ns max to be again plus minus 1 over square root of 2 multiplied by 1 over square root of 2. 1, 1, 0. Now, instead of the plus sign here, instead of the plus sign, I'm just going to use a minus sign. Again, 1 over square root of 2, 1, minus 1, and 0. So again, take this as a common factor. You will have plus minus 1 over 2 multiplied by 1 minus 1 is going to be 0. I have 1 minus 1 is going to be 2, and then I have 0 left at the bottom. And then the other possible direction is going to be plus minus 0, 1, 0. All right, so I'm just going to write my finding here as well. So the maximum shear stress is 100. On the same plane, I have 0 normal stress, and the direction of these planes is going to be plus minus 1, 0, 0, or plus minus 0, 1, 0. So I've got 2 sets of planes. All right. Now I want you to think, have a look into these results, and tell me if you find any interesting observations. I'll probably just summarize the results here. So I've got a summary for the results here. This is T1, T2, and T3, and I have N1, N2, and N3. All right, and then we have TS max and TM. I'll probably just copy the whole thing on one slide in the OneNote so that you can see everything. Here, I just make it slightly bigger. All right, can you see that? Is it clear? All right, in this case, I wanted to look into these numbers just to highlight them. So this set of numbers, this one, and this one. And then I wanted to look into N here and here. All right. So this one and this one. And by the way, you should have plus and minus in front of them. All right. So now look into these numbers and tell me if you see any interesting behavior in here. This one here, because I think this is also very relevant. Right, so when I look into this plane, I have these numbers in there. All right, so now tell me if you see anything that is worth noting or anything that is interesting about this result. That the maximum stress, the entire magnitude of the stress is 100. So you see 100 is appearing everywhere. Anything else? Probably first thing to do is just to write down the stress tensor, right? This is the 100. I just draw it below. So you have 0, 100, 0, 100, 0, and 0, and then you have zeros everywhere else. Now, I'm just going to draw things in 2 dimensions because if you look into the third dimension is really 0. There's nothing happening in there. So I'm just going to draw it in 2D. This is x1 and x2, and this is the square, which we have been talking about for a while now. Now, this is sigma 1, 1, this is sigma 1, 2, this is sigma 2, 1, this is sigma 2, 2, right? I'm going to draw them. So sigma 1, 1 is 0, so you don't have anything happening in this direction. This is 0 there, right? If you look into sigma 1, 2, so this is active on the plane number 2, and the direction is parallel to 1. So this is 100. This is the plane where I have the normal direction to be, but this is the plane where the normal direction, this is the plane. Yeah, this is the plane where I have the normal direction, or this is the plane identified by the normal direction of x2, right? This is E1, and this is E2. E1, sorry, this is E1, and this is E2. So the plane which is identified by E2 is this plane here. So the component should be active on this plane. Now the component is parallel to x1, so it is a shear one, so it is active in this direction. I'm just going to remove it. I'm going to draw the shear component because otherwise it's going to be too crowded. Okay, so you only have a shear component here, and this amount is 100. Now you look into the second one, this is T, or sigma 2, 1. It is active on the plane that is identified by x1, which is this plane here. And it is in the direction of x2. So it should be positive, 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 positive. It's in this one. Now, obviously for equilibrium, you need to have components active also on this plane and on this plane. So this is again 100 and 100, but this is active in the negative direction. This is double negative. If you look into the normal direction, this is opposite to x1. And if you look into the force itself, this is opposite to x2. So it is negative, negative, so it's going to cancel each other and it's going to be positive. All right, you agree with this? All right, now on this specific plane, you have the maximum shear. And these directions for this shear, the direction for this plane, is going to be this plane, this plane, this plane, and this plane. Now let us try and find what is the planes we have here. The first one, this one, is basically E1, so it's going to be 1, 0, 0. The second one, which is this guy here, is going to be 0, 1, and 0, because this guy here is parallel to the x2. This is E2 simply. If you look into this one here is negative E1. So it is basically -1, 0, 0. And if you look into the last one here, this is negative E2. So it is going to be 0, -1, and 0. Now, if you look into the direction we have been able to identify for the shear, you see that this is ±1 and ±1. This is basically the original stress tensor. This one here, and delete all these details and leave the 100. Oops. So the original stress tensor is actually representing a situation where the shear is going to be maximum. And all these planes are perpendicular to each other, just like we said. So it's happening on this plane. Yes, exactly. This is the one. Yeah. I mean, if you look into the first part of this example, if you look into this one, and if you look into the part where we did the eigenvalues, you see that in this example, we are trying to solve for a normal direction that is actually one of the eigenvalues, right? Is this one, this specific one. So if you try and do that, what you are going to get the eigenvalue. It's basically, you have the plane for the eigendirections, you have the plane for the principal direction, and you try to find the value of the normal stress on this plane. The normal stress is going to be 100. And it's going to be purely normal. There is no shear component to that, because you are just using the same direction. You're just identifying the normal. You are identifying the principal direction, and you are using that to find the normal stress. So it's going to be purely normal. Now, obviously, if instead you use this one, you are going to get this value for the normal stress. And if you use this one, you're going to get this value for the normal stress. And if you want, you can try that. Now, this is going to be the normal stress, and the shear is going to reflect that. So on this plane, you'll also have 0 shear stress, and on this plane, you'll have the maximum possible. Okay, so it's just going to be a combination of both things. All right, do you have any questions about this example or what we have been discussing so far?
Not always be the case then. But the eigenvalue is always going to be the same as the normal shear stress. So it's just in this example.
No, in this example, because I specifically asked you at the beginning of this example to find the magnitude of the shear on this specific plane. I'm asking you specifically about this specific plane. Now, I picked this plane because it is the principal direction, but it can be something else. Let us then move to the next example. For the next example, I want you to do that yourself. It's exactly the same thing, slightly more numbers in there. So it's, the one I solved is quite sparse, but this one is a bit more dense. There's more numbers in there to do calculations for. So I want you to find the principal stresses and the principal directions and the maximum shear stress and the normal to its place, basically where this maximum shear stress is active.